right, welcome guys. Good to see you. Today, we're going to review, and you've got two massive giant review sheets at the tail end of that packet. You have one that is titled the in-class review, which in theory we started working on last week, Thursday. The people that were here, the A people, for sure were working on it because they were in front of my faces. Not my face, I only have one face. The people that were at home, I hope you maybe started it or we're trying some of these problems. But what I want to point out before I go over any of these, and before we start trying to just practice some problems, and you guys can ask me some questions, obviously, is this. At the front end, and I'll show the people online too, okay? At the front end of the regular review sheet, or whatever you want to call it, you have a page that looks like this, and it says topics on the Unit 3 test. This goes through a brief synopsis of literally everything you need to know from every single topic throughout the course of Unit 3. It's two-sided because Unit 3 is a beast, the biggest unit we have all year. Or it's tied maybe for the biggest unit we have. It's a big unit, right? So this is a two-sided like note sheet, more or less, of like everything in this unit. So you'll notice 3.1 is huge because we spent like 4 days on 3.1, if that rings a bell. And what I'd recommend, if you have not read through this, read through those 2 pages and use that as like a study guide or like a launching point for what you know and what you don't know. You know what I'm saying? Like as you're going through all these bullets, it's like, oh, ideal gas law problems. Okay, that was PV equals nRT. That wasn't too bad. I think I know how to do that. Maybe I'll just look at a problem or 2, but I'm good, right? Whereas you look back and it's like, huh, what the heck is London dispersion again? Right? And that's a bigger issue. Maybe you should go back and take a peek at that. But anyway, I do this every single unit. I outline what you got going on, and it was there for Unit 1 and Unit 2. I hope you found it then. I kind of pointed it out, but maybe you did or did not find it. But I think this is useful. I think this is helpful, at least at the very least, to give you an outline of what's expected and what you can assume you'll see on tomorrow's test. And then the rest of it, there's another 3.5 pages of review fun for the regular review sheet. So there's a ton that you can look at. Now, these aren't assignments. They're not due, so to speak, but you do have a test tomorrow. So it's in your best interest, probably at a minimum, read them all, right? Jot something down or contemplate it a little bit and cross-reference the answer. The answer key is posted, okay? I have posted the answer keys to all 3 homework assignments. I have posted the answer keys to both review sheets. So you have answer keys to all of the practice work and all that you've done and that you will do in theory over the next 24 hours to get ready for the test. Okay? So all I'm going to do today, gentlemen at home, if you're hanging out, I am going to go through some of these problems and some of these answers as the hour goes along, but really, this is your hour to study. Please use the hour. Use me. I'm here, right? Please ask me questions. I'm happy to want to help. That's all I got. Yes, well.
Can you use like a notes that you put on the last test or no?
Yeah, because again, I mean, honestly, like everything's open note this year. I can't really, there's no other way I can do it, right? Because if a kid's at home, and I have absolutely no clue what they have or don't have in front of them. So, yeah, assuming you can navigate, right? That's the hard part with open note tests is you still only have an hour. So it doesn't really bother me that it is open note, and it is, and yeah, I'm not going to give the kids at home an advantage over the kids here. That's not fair. So, yep, you can use whatever the heck you want to use, assuming that's within reason. Obviously, you can't have your cell phone out and like, But I don't even know if that would matter either way, because honestly, like again, the timing of it's a long enough test where like an hour is going to get real short if you're looking up every answer. Yeah. All right, cool. Try some of these problems. I don't know if you guys tried them at home. Like I said, I hope you did. And if you're good, you can bust out a Chromebook and check some answer keys, and I'll go through some of these. And if you have specific questions about a specific problem, I'm happy to address any of these and go over the answer, how I got there, the thinking. I'd strongly recommend too that you also have your formula packet out, right? Your periodic table sheet followed by your 2 consecutive sheets of formulas, because there's a smidge of math. We did use some of these this unit, which was fun. And then I'll let you guys get ahead, and then I'll talk about some of them. And I'll be sure to take attendance for all 4 of you. Done. Nice. And I know we're supposed to be distance and all that good stuff, but honestly, if you need to talk to each other, or just if you want to like sit, 6 feet apart and talk and converse and go over some of these together, that's perfectly fine. They were doing that last week Thursday. It was kind of nice. I felt like normal school. But there was kid stuff. Shut up the water fountains up here. They're on the second floor, aren't they? Yeah. That was odd, yeah.
I thought they were all besides the one.
I'm almost positive the one on the second floor was somewhere up on the second.
I don't know what.
I mean, they have the water bottle filling one that works for sure, but oh well. I'll just sip on my little bit before I have left. And guys at home too, if you have a question, obviously you can chime in and I'll be happy to go through it. Because in grand total between digital and real life, there's 6 people. I think I can handle it. I think. All right, let me do some of you. I'll start going through a couple. Okay. So for number 1 here, we're trying to identify the strongest type of intermolecular force. What that's trying to imply is that there might be multiple, right? Some of these, or everything I should say, has London dispersion forces. Every single substance has London dispersion forces. Okay? And And London dispersion forces, just to recap, those are the ones where they're very weak because essentially they just occur because the electrons are in constant motion. And when the electrons are constantly moving around, essentially at some point in time, they become unequally distributed. You get these tiny little partial positive regions and tiny partial negative regions. And then between that and the neighboring molecule, we have these extremely small partial charges that just kind of come around because of the motion of electrons. Those are London dispersion. Everything has them. They're super weak. Okay? There are stronger types though, right? So let's start here, HBr. Now, a big chunk of the intermolecular forces discussion has to do with whether it's a polar or a non-polar molecule. Now, that conversation is a lot of Unit 2 stuff. It's, okay, well, what's the electronegativity? What's the shape, right? We might need to do a Lewis diagram every now and then to figure out the type of intermolecular forces we have. But for the first one here, it's HBr. It's a line, right? It's one atom, two atoms, and they're bonded together. However, bromine is more electronegative than hydrogen, and as a result, we do get a polar molecule. When it's polar, you're guaranteed that it is at least dipole-dipole. It could be stronger than that, though. The other type is hydrogen bonding. Hydrogen bonding occurs when you have a hydrogen covalently bonded to fluorine, oxygen, or nitrogen. Got to be one of those three. If it's not one of those three, it's not hydrogen bonding. So even though this molecule has a hydrogen, it's not bonded to one of those three. Oh, this is going to totally just go in a cell. See that? Well, here's the answers. Oh well. So this is dipole-dipole because it's polar. Okay. For the next one, we have water. That has hydrogen and oxygen. Oxygen is more electronegative. This is a bent molecule, if we were looking at the shape and doing all that good stuff. It's polar. And it has hydrogen bonding because now I have a hydrogen or multiple hydrogens bonded to oxygen. And that's one of the three. The next one, carbon dioxide. This one's a little sneaky. We've drawn it out a couple times. But carbon dioxide is a linear molecule. And because it's linear, with carbon in the middle, and oxygen on that side, and an oxygen on this side, those two oxygens are more electronegative than the carbon, but they end up canceling out because of the shift. So this ends up being nonpolar, and all you have is London dispersion. Okay? So that kind of question right here that we did for CO2, that's honestly like, that's the hard one, because you need to know the shape of that thing to get the answer correct. Because if we just looked at electronegativity, oxygen is more electronegative than carbon. But it's the linear shape of that molecule that makes it a non-polar molecule. Because one oxygen and the other oxygen cancel each other out. Okay? KBr, this is ionic. Now, ionic bonds are not an intermolecular force, so I'm doing a little bit of a, it's a little misnamed, so to speak, right? But ionic compounds can get sprinkled in these types of questions, and you just have to recognize it as ionic. Now, how can we find an ionic compound? What are we looking for? What was your definition from last year? Metal, non-metal. Yeah, it still works. It still works. There's your metal, there's your non-metal. That's ionic. Okay? Now, the other thing we have to look out for is polyatomic ions. A polyatomic ion, like off of the back of last year's periodic table, is also an indication that you have an ionic compound. Okay? So metal, non-metal, or something with a polyatomic ion. Those are ionic compounds. This guy, that's some organic molecule. That's ethanol, actually. Okay? Now, when you look at these organic molecules, the formula gets written in a way that kind of shows how it's bonded. OH at the end means that I have an oxygen and a hydrogen bonded together. Now, because the oxygen is there, it is polar. And because that hydrogen is bonded to that oxygen, it is hydrogen bonded. Okay? If you have nothing but carbon and hydrogen, it's non-polar. And all you've got is London dispersion. So again, I'll reveal the other side too, just for the sake of while we're here. All right? You want to be on the lookout for ionic compounds, because that's going to trip you up. If you don't recognize that it's an ionic compound, you're going to end up calling it one of these three, and it's not going to be right. Okay? After that, we want to consider, is it polar, is it nonpolar? If it's nonpolar, all you got is London dispersion, or LDF. We abbreviate it sometimes. If it's polar, you've got dipole-dipole. And you might have hydrogen bonding. It just depends upon what the hydrogen is connected to. If the hydrogen is connected to an oxygen, it's hydrogen bonding. If the hydrogen is connected to a bromine or something else, it's not, right? It needs to be fluorine, oxygen, or nitrogen. That's what you're doing. I'll leave this up for a second. Keep trying. If there's one you want to see, right? And this, again, guys at home, if there's one specific problem, you're like, hey, can you please go through that? We'll be more than happy to. Okay? Even if you haven't tried it, I don't care. We're here. I can help you. But if you're like reading them and it's like, ooh, whoa, 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 I have no clue how to start that. Check it out. Ask me, yeah, look.
The last one, why would that one not be hydrogen bond?
Okay, yeah, and I honestly, I would accept it because you guys aren't familiar with organic chemistry. Okay, so I won't do this to you tomorrow because this one's a little sneakier. Okay, the way this is written out is different than this one. If you notice, this one specifically is showing that the oxygen and the hydrogen are bonded together. With the way this one is written, and again, you haven't had organic chemistry, but in this format, I can tell you that this is like a 3-carbon chain, and that oxygen is connected to the carbon, not the hydrogen. Now, having said that, again, you're not familiar with organic chemistry, so I would accept that. It's wrong. This is correct. But again, that's kind of beyond what we've learned. That makes sense. I will not give you an example like that tomorrow because that's just not necessary. But sometimes these review sheets, I get a little excited, and then I give you some harder ones. So again, keep looking through. If there's something you want to see, and guys at home too, if there's a number you want me to go over, please let me know. I will go over it happily. Or angrily, I don't know. Whichever. And don't feel like you have to go in order. If you don't like number 2, cool, skip it. Go to number 3, right? Or work backwards. I don't care. I just want you to try them all or look at them all before tomorrow. It will help you immensely. Yeah.
I'm gonna, like, not to confess you, but other review sheet, I was doing looks like a solid, like, kind of
Yep.
and there's like, NE is group 8A solid, you get some molecular.
No, you don't. So that was the only crossed off. So if you remember back on that day, so 3.2, on the very front of that 3.2 note sheet, we had like the little web, the word web, and that was like the very bottom right-hand corner when we crossed it off. So no, I will not ask you that at tomorrow's test. Yeah, it's something that used to be a part of AP, but it's kind of such an obscure case that they've just kind of ignored it now. Is there one you'd like me to go over? Or something I can help with? Anything. Make me do things, please.
Number 12.
Sure, let's take a look. Yeah, okay. So this one's kind of a two-part situation. The first part is kind of review from old units. First part is, hey, can you identify which circle represents which ion? And then the second part of this is actually what's like related to unit 3, which is if I were to dissolve these ions in water, like how would the water molecules orient themselves after these have dissolved? Okay, so let's do the first part. Here's our ions. We have sodium 1+, fluoride 1-, and magnesium 2+. This is element number 11, element number 9, element number 12. But when they are ions, all three of them have the exact same number of electrons, right? Sodium 1+ has lost an electron. It's down to 10. Fluoride 1- has gained an electron. It's up to 10. And magnesium 2+ has lost 2 electrons. It's down to 10. All three have 10 electrons. So what's going to determine the size is the number of protons. Okay? If the electrons are the same in all three, we have to look at how many protons each has. The one with the most protons is going to be the smallest, right? Because there's more protons in the nucleus, essentially the attractive force draws in those outer electrons more tightly. So I would totally expect that this is your magnesium 2+, this is your sodium 1+, and this is your fluoride. And again, it is 100% based off of the protons because the electrons are all equal. 10, 10, 10. That has 12 protons, it's the smallest. This has 11 protons, this has 9 protons. Okay, that's the first part. That's actually old, right? That was unit 1 or unit 2 stuff, maybe? I think unit 1, actually. The second part is, here's a little water molecule. If I were to dissolve fluoride in water, how would the water molecules orient themselves around that ion? Well, I'll put this one down below. This is negatively charged. What is going to be attracted to the negative charge? The partially positive hydrogen, right? So when you look at the water molecules, where's my pen? Okay, this is oxygen. Those two little ones are hydrogen. These are partial positive. The oxygen is partial negative. Now, the reason why they are that way is because of electronegativity, right? Oxygen is more electronegative. It pulls the electrons towards itself. You get a partial negative charge. So when the water molecules dissolve these ions, we would totally expect these waters to orient themselves where the partial positives are facing the negative ion. So this ion would be surrounded by tons of little water molecules. All of the water molecules would have the hydrogens facing towards it because opposite charges attract. For the other two, it's the exact opposite, right? Now, because these are positive cations, I would totally expect the negative or the partial negative oxygen of the water molecule to be facing that ion. So this one would be surrounded by water molecules with all of the oxygens facing towards that ion. Does that make sense? Cool. Any other follow-up questions? I didn't finish my picture here, but you get the idea, right? I can keep adding more of these if I want and changing them. And oh, look there, now it's down here.
On the test roll, mean, all the electrons are the same.
Oh, I won't, so I will not ask you a question about size on the test. This is an example of my review sheet nonsense where I'm like, that's old stuff. You should know what that is. I'm going to sprinkle it in just for fun to keep you on your toes. But yes, I would ask a question about like what's going on with the ions in the water, but I wouldn't necessarily ask a question about the size of the ions. I'm just asking. Okay. Another one. Make me do things. How's the math looking? How's the ideal gas law? How's the electromagnetic radiation calculations?
Electrons like the one.
Yeah, that's electromagnetic radiation stuff. You want to look at like 16 or 17 or whatever? I forget what number they are.
15.
Sure. Sure. What is the frequency of a photon with a wavelength of 0.333 nanometers? Identify the type of electromagnetic radiation by referencing an electromagnetic spectrum. All right. Okay, what do we know and where are we going, right? That's kind of the first thing we always want to identify with any problem. We want to solve for frequency, and we've been given wavelength. We have an equation that allows us to compare those two values. This equation from your packet. C equals lambda nu. C is the speed of light. It's a constant. You can look it up. It's in the packet. Right next on the other side, right? 2.998 times 10 to the 8th. Lambda, the upside down y, is wavelength. We have wavelength, but it's currently in nanometers. We're going to have to fix that. Nu is frequency. That's what we're trying to solve. So let's set this up. Let's convert our nanometers first, because that's not going to work. The speed of light is 2.998 times 10 to the 8th meters per second, right? We need the length unit to match. If it doesn't match, we're just making things up. So let's convert our nanometers to meters first. Okay, you wouldn't have to show me this conversion by any means, right? Because it's all digital, so you'd have to just do it off to the side or do it in your calculator or do it in your head. But we're here, I'll show what it looks like. There are 1 times 10 to the 9th nanometers in 1 meter. So when I do this, I'm going to shift my decimal 9 places. Okay? And just so I don't screw it up. Times 10 to the negative 10. This is horrible. Why did I write it so far to the right? Okay. 3.33 times 10 to the negative 10 meters. So now I'm going to set up my equation. We'll switch color just for fun. Nice forest green. It's not dark enough. Let's go dark. Ooh, yeah. Brilliant stuff. All right, 2.998 times 10 to the 8th meters per second equals wavelength, which is 3.33 times 10 to the negative 10 meters, multiplied by frequency, which we don't know. That's what we're trying to solve. Now the algebra is as easy as life gets, right? 0.998 times 10 to the 8th divided by 3.33 times 10 to the negative 10. And I'm getting a frequency equal to 9.00 times 10 to the 17th. Times 10 to the 17th what? What is frequency measured? Well, what are we left with, right? If I divide meters per second by meters, the meters is going to cancel out, right? So what am I left with? I'm left with 1 over seconds. But that's a weird unit. So they've given it a special name. And they call it hertz. Okay? Make sense? Easy peasy? All right, sweet. Keep them coming if you want to. And it doesn't have to be on the in-class review. If there's something on the other review sheet that's bothering you, I can try to bring that up too, and we can go through a problem over there. I don't care. Sure. I don't have a PowerPoint for it or a smartboard for it, so let me do this. Just add a blank slide and follow through it this way. Number 14, you said? Oh, okay. Yep. So for number 14, we have a picture, actually. I'll draw it. What the heck? I'm a great artist. That. Looks like that for the first beaker, right? Looks something like this. Now, if you look at the answer key for this one, I have written down sodium chloride, and I think this is lithium. What did I put? I don't have it open. Oxide, maybe? I don't know. Lithium oxide, so Li2O. Okay. Now, are these the only answers that work? Absolutely not. I think that's maybe where people are getting confused on this one, because I've been asked about this earlier today too. What I'm looking for with this picture is give me an ionic compound that has 1 plus, 1 minus ions. It could be any 1 plus, 1 minus combination. So I had sodium chloride. That's fine. Could have been lithium fluoride or potassium bromide or whatever. Okay, there's a whole bunch of choices. As long as the cation you pick is a 1 positive cation, and as long as the anion you pick is a 1 minus anion, you're good, and it's correct. For the other one, same thinking, right? I have a 1 plus cation and a 2 minus anion. Pick something that has a 1 plus, lithium, sodium, potassium, okay? And pick an anion with a 2 minus, oxide, sulfide, whatever that might be.
It's Li2O.
Yeah, correct. Yeah, so there's a total of like 2 molecules dissolved, right? In theory, if I were like to group them, here's one grouping, right? That would be like one of those. Here's another grouping. But that doesn't matter. I mean, the formula or the ratio is 2 to 1. Yep. See, I'd like to do this with like the entire year's curriculum. And you guys just pick random questions out about the curriculum and test these. Yeah, that'd be so much fun. Like, I would genuinely enjoy that. Probably why I teach this class, but I don't know. It sounds like a good time. I enjoyed the trivia this morning though too. That was kind of, I'm into trivia. They should do that every day for the morning. It'd be so much more fun than just like sitting there staring at you guys' phones for 10 minutes.
I did that last week too.
Yeah, I was gone that day, but yeah, apparently they did. That was Thursday, I think they did that. I take my daughter to her annual doctor appointment, which she was dreading. She was literally like crying and screaming about it earlier in the week. Then I took her there. She gets her 3 shots, and she doesn't even cry. And I'm like, so we're gonna literally cry over this because you don't want to go to the doctor. You're screaming at me on Tuesday. I take you there on Thursday. You get 3 shots, and you don't shed a single tear. Like, okay, have that one up. I don't know. My daughter's kind of an enigma. I don't quite understand her. It's the most confusing human I've ever known. In a positive way, I'm sorry. I love her. She's just crazy. Guys at home, you got anything for me? Where'd you leave? Are you still there? Well, they're still there. You're on the big screen now, boys. Wave. Wave to the 4 people. And I know you can go on and I know you can cross-reference this, right? So again, it is all posted, so it's all there. You just got to go digging for it on its learning. I posted it in the plan, so you shouldn't have to go to the resources tab. It should be right from your face, right on the front page. And I do strongly recommend going back to your homeworks. Okay, I do grade them obviously, and I give you grades off of like my key, but you know, like it's hard to give individualized feedback and like correct answers, wrong answers in a digital format. So if you've lost some points or something like that, or it's been a while, obviously, on those 3 assignments, I would recommend going back and looking for those keys tonight too, just to kind of get a sense of what you screwed up maybe. You'd have to cross-reference your sheet with the key, but it's all out there. Sure. Number 10 on the regular review. So if the following gases are all at the same temperature, that one? Yeah. Okay. Sure, let's make a new slide. All right, this is number 10 from the normal review sheet. And it says, if the following gases are all at the same temperature, which of these would have the fastest moving particles? Explain your answer. Our options are carbon monoxide, sulfur hexafluoride, carbon tetrafluoride, and neon. Now, when it comes to how fast the particles are moving, it depends upon a couple things. It depends upon the temperature. How's it going? You here to bother me or what? Oh, okay. Good. You need something? Yeah, no worries. No, I'm working on yours too. This is what happens. People miss this class when they're out of it, I swear. Maybe that sounds like the most absurd statement you've ever heard in your life. Maybe, I don't know. Anyway, okay, so these are our options. Now, when it comes to the speed of the particles, right, it comes down to this equation. And this equation is in your formula packet. We just don't mathematically use it, as weird as that sounds. Okay, so the kinetic energy is equal to 1/2 the mass times the velocity squared. That's all well and good. If you take physics, you can solve for that pretty easily. It's not a hard equation to solve for. But what I want to focus on is this chunk. I'm on this side of the board. I might as well move that over here. Okay, this portion right here. That's trying to say that mass and velocity have an inverse relationship. Meaning that as mass goes up of a particle, the velocity of that would have to go down in order to make it mathematically the same number. If the velocity were to increase, that means the mass would have gone down. Okay? So here's what we're really looking at with these. Assuming the temperature is the same, which in this problem it is, it says it is, we'd have to focus on the mass. The bigger the mass, the slower the velocity. The smaller the mass, the bigger the velocity. What we're looking for is the lightest gas of all 4 of them. So if we go to our periodic table and start looking up our molar masses, carbon monoxide, that's a mass of 12.01 plus 16. 12 plus 16 is 28, right? Can I do math? Ish. I'm not doing sig figs. I'm just spitballing a little bit. Sulfur hexafluoride. Sulfur is 38. What is it? 32? Yeah, 3206. And then fluorine is 19, but we got 6 fluorines. That one's big. Okay? Doesn't matter. Bigger than the other one. This one too, right? 4 fluorines. Each fluorine is 19. This is big. I'll use a lowercase b to signify that it's less big than the other big one. Neon. I look up neon, and neon is 20.18. Now, the one with the lowest molar mass or the smallest mass has the greatest velocity. That's our guy. Okay. I could phrase that completely backwards if I wanted to, right? I could say which of these has the slowest velocity. Well, then you're looking for the biggest one, right? So either which way, the equation is this. We don't mathematically solve for it, but do understand that just because two gases are at the same temperature does not mean that their particles are moving the same speed. And if you need help remembering that, you can think about a helium balloon. You breathe in helium and your voice gets really high. The reason why your voice gets so high is because those helium particles are moving faster than air. They're lighter, they're smaller, and they have a greater velocity. And that's why your voice gets so high when you suck in helium. Okay? Cool. Good. I don't know why they don't move this to like a storage area. But. Now, 10 minutes. Can I do some more? Can I help you with another one? In class? Sure. Oops. I'll make a new slide. All right, 16 and 17 from the normal review. What do we got? Sure, okay. So for number 16, the question is, which is more soluble in water? Dimethyl ether, which has a formula or a formation of that, or ethanol, which has a formation of that. So we're trying to dissolve both these things in water, and the question is which is more soluble? In other words, which of these mixes better with water? Well, it's going to come down to the types of intermolecular forces that exist, and that's what my hint after that is, right? I give you a hint in the next sentence. It says, consider the types of intermolecular forces that it would form, and then explain your answer. Okay. So water, we know is H2O, right? And if I were to draw it out, it looks like this. And there's an oxygen in the middle, and there's 2 hydrogens on either side. There's a couple lone pairs. This is partial positive, that's partial negative. Forms hydrogen bonds, right? Dimethyl ether looks like this. There's an oxygen in the middle, a carbon on one side with 3 hydrogens coming off of it, a carbon on the other side with 3 hydrogens coming off. Okay? Polar or non-polar? Start there. It is polar. Now, it's a little sneaky, right? Because it looks like if the whole thing was linear, it would look like, oh, well, it's symmetrical, right? That side's got a CH3, that side's got a CH3, but it's bent, right? That oxygen makes it bent, much like the water is bent, okay? So really, you would replace like this with a CH3 and that with a CH3, and it's the same sort of structure. So it is polar. What type of intermolecular forces would this thing have? If it's polar, what kind of intermolecular forces would it have? It's got dipole-dipole. Do we have hydrogen bonding? Exactly. There is no hydrogen bonding. And the reason why there isn't is because that oxygen is only attached to carbons, right? In order for hydrogen bonding to exist, we need to have a hydrogen bonded to an oxygen, fluorine, oxygen, or nitrogen. So this has dipole-dipole. The other molecule, we have 2 carbons in a chain. This one with 3 hydrogens, that one with 2 hydrogens, and then we have an OH group at the end. For ethanol, what types of intermolecular forces would ethanol have? That's for everyone, not just you. Well, okay, let me slow down. Is it polar? Or is it polar or non-polar? It's polar. We have an oxygen there, right? Again, the dead giveaway with organic molecules. And when I say organic, I mean anything with carbon, hydrogen, oxygen. Okay? With those types of molecules, if it's just carbon and hydrogen and nothing else, it's non-polar. If there's something else there, if there's an oxygen there, it's going to be polar. It's going to be polar. Oxygen is very electronegative. It throws the whole structure off and it makes it polar. So it's polar. We have dipole-dipole at a minimum, right? Do we have hydrogen bonding? We do. We do, because we have a hydrogen covalently bonded to an oxygen. So this is hydrogen bonding. Now, water, we know, let's get ugly, is hydrogen bonding. Okay? They don't have to be the same type, but here's what that means. Okay? When you have hydrogen bonding, what that's trying to tell us is that we have bigger partial charges. Okay? London dispersion forces, very tiny partial charges. Dipole-dipole forces, a little bit bigger partial charges. Hydrogen bonding, even bigger partial charges. Bigger partial charges means stronger attractive force. That's the whole Coulomb's law thing, right? We haven't talked about Coulomb in like 5 days. It was about time to talk about it again. Okay. Bigger charges, stronger forces. So ethanol, with its hydrogen bonding, would have bigger partial charges, leading to stronger attractive forces with water. The ethanol is going to mix better or is more soluble in water than the dimethyl. Okay? It comes down to the type of intermolecular force, and it comes down to how big the partial charges are. That's a tough one. That one takes some thinking.
So for like 17, is that the same concept then? Would it be like just whichever of the 4 options has strongest forces?
Here's what's going on in 17. Now, in this one, we have polar, right? Polar mixing with polar. Polar things mix with other polar things. Non-polar things mix with other non-polar things. So here's the weird thing with 17. In 17, we're looking for the exact opposite. What we want to mix with our octane, which is C8H18, which is a non-polar molecule, right? We want something non-polar. Because what happens is if you try to mix polar substances with non-polar substances, the polar substance just sticks to itself. When you mix water and oil, the water and oil separate because the water is so strongly attracted to itself that it doesn't even want to mix with the oil at all. So polar substances mix, non-polar substances mix, which means in 17 we want to find the one that's the non-polar substance. So water on the end is very polar, obviously. NH3, which is ammonia, it's also polar. Okay? It has a trigonal pyramid shape, if you remember from Unit 2. And then the next one is sulfur pentafluoride, also polar. That is a square pyramid shape. Okay? And the middle one there is CF4, which is carbon tetrafluoride. That's the one. Carbon tetrafluoride is a tetrahedral shape. It's a non-polar molecule. And because it's non-polar, it would mix with our non-polar octane. So yeah, kind of same concept, but the exact like flip of it. The complete opposite of what's 16. Five minutes, what can I do? Give me one more.
Could you go over 9A real quick?
The in-class or the other one?
Oh, the in-class.
Okay. Then we'll try to get to yours too. Liza. 9A. Sure. This one's quick. All right, so I have a Maxwell-Boltzmann distribution. Now, these graphs are basically just showing probability of particles or the population of particles at any given speed, okay? What this one's asking is I have 4 gases all at the same temperature. Because they're all at the same temperature, their differences in velocity are going to come down to their mass, all right? So with their mass, by the way, the height of the peak is not the speed, right? Please be aware of that. That is the #1 way that kids screw this up, is they think the height of the peak is the speed of the particles. Speed is on our x-axis. Do you see this little shallow blue hill? These are the fastest moving particles on average because their height, their peak falls right about there. The yellow is the next fastest, then this light blue, or cyan is sus, okay? And then the purple one. Are you smiling behind your mask?
Yeah.
Okay, good. It's always cyan. The peak is your average velocity. So the blue, the dark blue here is your fastest, then yellow, then light blue, and then purple. So what we're looking for here is the one that's moving the fastest in this set should be the one with the lowest molar mass. The one that's moving the slowest should be the one with the highest molar mass. It's that whole mass-velocity relationship with gas particles. Kinetic energy equals 1/2 mass times velocity squared. Mass goes up, velocity goes down. Mass goes down, velocity goes up. And when you interpret this graph, the peaks are representing the velocities, where they are left to right on the x-axis. All right. Which one? 8? Try my best. Is it quick? Oh, yes, it is quick. Okay. Now, ideal gases are gases with 0 intermolecular forces of attraction. So what we're looking for is the absolute weakest intermolecular forces present. These all, with the exception of HCl, HCl is polar, right? So this is going to have dipole-dipole. But these 3 are all London dispersion. So now the question is, well, which one has the weakest intermolecular forces? Bigger mass, more electrons, equals more polarizable. As polarizability goes up, intermolecular forces increase. They get stronger. So if I look at the mass of neon, it's 20. If I look at the mass of argon, it's 40-ish. I don't know if anyone has the periodic table. The mass of krypton, even bigger. Okay. So neon has the smallest mass, and therefore the least number of electrons, and therefore it has the weakest intermolecular forces. It's the most ideal. The word ideal means 0 intermolecular forces. So we want to get as close to 0 as we possibly can. This one's dipole-dipole, it's out. These are both London, or all 3 of these are London dispersion. So now it comes down to, well, which of those has the least polarizability? Which of those is the lowest number of electrons? All right, thank you for your attention. I'll clean up your areas with the wipes. Have a lovely day, guys. Gentlemen at home, thanks for joining me. We'll catch you later. Test is tomorrow. Please study. Plenty to look at. All the answer keys are posted.